How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You hear the headlines all the time. They pop up in your news feed, sandwiched between an article about a new phone and a viral video of a cat. Quantum computing breakthrough paves the way for new medicines. Experts warn quantum computers could shatter modern encryption. The quantum revolution is coming. The words feel heavy, important. They promise a future that is radically different, a world where diseases are cured overnight, where new materials with impossible properties are designed in a lab, where the very foundations of our digital security could crumble. And we nod along, because it sounds incredible. It sounds like progress. But if you're like most people, right after you read that headline, a quiet question forms in your mind. What does that actually mean? What is a quantum computer? The explanations we get are usually vague and metaphorical. They talk about harnessing the power of atoms, about computers that can be in multiple states at once. It sounds less like engineering and more like a Zen koan. It feels like magic, a technology so advanced, so far beyond our daily experience, that it's indistinguishable from it. We treat it like a black box. We see the promises written on the outside, miracle drugs, unbreakable codes, artificial intelligence beyond our wildest dreams. And we accept that the inner workings are the domain of physicists with rooms full of chalkboards, speaking a language we can't possibly understand. We assume the complexity is irreducible. But have you ever stopped to wonder how that actually works? If we stripped away all the jargon, all the mind-bending physics, what are the fundamental rules that make a quantum computer possible? What if the core ideas aren't impossibly complex, but just beautifully strange? What if we could understand them not with advanced mathematics, but with a simple analogy like a spinning coin? This is First Principles, the podcast that deconstructs the invisible systems that run our world. And today, we are opening that black box. We're going to look past the hype and the mystery to find the simple, foundational truths of one of the most profound and promising technologies ever conceived. Today, we're going to understand the quantum computer. Before we can pry open the box, let's spend a moment appreciating just how magical it seems from the outside. The story of quantum computing isn't just about making computers faster. We already do that. Every year, our laptops get a little thinner, our phones a little quicker. That's classical computing, and it's a story of refinement, of making things smaller and more efficient. A supercomputer today is, at its core, just a gigantic version of the phone in your pocket. It's faster, yes, but it thinks in the exact same way. It thinks by checking things off a list one by one, just very, very quickly. Imagine you're trying to find the perfect recipe for a new kind of cake. You have a massive library with billions of cookbooks. A classical computer, even a supercomputer, would work by pulling the first book off the shelf, checking every recipe, then putting it back and pulling the next one. It might do this millions of times a second, but it is fundamentally a linear, brute force process. There are certain problems in the world that are just too big for this approach. The list is too long. The library is too vast. These aren't just slightly harder problems. They are problems of a completely different species. For example, designing a new drug. A new medicine works by binding to a specific protein in the body, like a key fitting into a lock. The challenge is that a single, moderately complex molecule can fold itself into a staggering number of possible shapes. To simulate just one of these molecules to find the perfect key, would require a classical computer to check a list of possibilities larger than the number of atoms in the known universe. Our fastest supercomputer could run from the Big Bang until the end of time, and not even make a dent. This is where the promise of quantum computing enters the room. It doesn't just promise to check the list faster. It promises to rewrite the rules of how you search the list. A quantum computer, in theory, could look at every single one of those molecular shapes, all trillions upon trillions of them, simultaneously. It's not like reading all the cookbooks one by one at lightning speed. It's like being able to absorb the information from the entire library in a single instant. This one capability, this idea of massive parallelism, is the source of all the revolutionary promises. It's why scientists believe quantum computers could help us design new catalysts to pull carbon from the atmosphere, or create materials that conduct electricity with zero loss of energy at room temperature. It's why cryptographers are terrified. The security that protects your bank account, your email, your government's secrets, is based on a mathematical problem. Finding the two prime numbers that were multiplied together to create a very large number. For a classical computer, this is like trying to find two specific grains of sand on all the beaches of the world. It's practically impossible. But for a quantum computer, it's a problem with a structure it's uniquely suited to solve. It could, in theory, sift through all those possibilities at once and find the answer with terrifying speed. So, on one hand, we have the promise of solving humanity's biggest challenges in chemistry, materials science, and medicine. On the other, the threat of a global security breakdown. It's a technology that feels almost mythical in its power, and it's this immense world-altering potential that makes the black box so intimidating. How could a machine possibly do what we just described? How can anything look at a billion things at once? The magic we see feels too profound to have a simple explanation, but it does. And to find it, we have to start with the simplest component of any computer that has ever existed. To open the box, we have to go back to the most fundamental concept in all of computing. The first principle. It's not a silicon chip or a line of code. It's a single, simple idea, the bit. A bit is the smallest possible piece of information. It can only have one of two values, yes or no, true or false, on or off, 0 or 1. Think of a light switch. It can be in the up position, or it can be in the down position. There is no in-between. Our entire digital world, from the phone in your hand to the global financial system to the servers that host this podcast, is built on top of this one gloriously simple binary concept. Billions and billions of microscopic light switches, all flipping on and off, representing zeros and ones, to create everything you see on a screen. A classical computer is just an incredibly sophisticated machine for flipping these switches according to a set of rules. It's reliable. It's predictable. A switch is either on or it's off. A 0 is always a 0 and a 1 is always a 1. This certainty is the bedrock of computation. For over a century, this has been the undisputed first principle of information. And now, here comes the record scratch moment. Here comes the question that opens the door to the quantum world. What if that wasn't the only way? What if a switch didn't have to be just on or off? What if it could be both? This question sounds nonsensical in our everyday world. A light switch can't be both up and down. A coin can't land on both heads and tails. These are mutually exclusive outcomes. But at the subatomic level, the world plays by a different set of rules. the bizarre, counterintuitive, but rigorously proven rules of quantum mechanics, and it's down there in that strange realm that we find the heart of the quantum computer. We find the replacement for the bit. It's called a qubit, a quantum bit. And here is our core analogy for the rest of our journey. If a classical bit is a light switch, a qubit is a spinning coin. Imagine you flick a coin into the air. While it's spinning, tumbling end over end, what is it? Is it heads? Is it tails? In a way, it's neither. It's a blur of possibilities. It has the potential to be heads and the potential to be tails. It exists in an indefinite state, a combination of both outcomes. Only when it stops, when it lands on the table and you look at it, only then does it resolve into a single definite state, heads or tails. This is the first, most crucial principle of quantum computing. It's called superposition. A qubit, just like that spinning coin, can be a 0, it can be a 1, or it can be a blend of both at the same time. It's not 50% of each, necessarily. It could be 70% likely to be a 1 and 30% likely to be a 0, or 1% and 99%. Think of it as a dimmer switch instead of a light switch. A light switch is either 0% on or 100% on. A dimmer can be at any percentage in between. The qubit holds all those possibilities within itself simultaneously. This one idea is the source of the quantum computer's power. Let's see why. One classical bit can store one of two values, 0 or 1. That's it. One qubit, because it's in superposition, can represent both 0 and 1 at the same time. Now let's add another. Two classical bits can store one of four possible combinations. 0, 0, 01, 10, or 11. But at any given moment, they can only be in one of those four states. Two qubits, however, because they are both in superposition, can represent all four of those combinations, 0, 0, 01, 10, and 11. Simultaneously, they are in a combined state that is a blend of all four possibilities. Add a third qubit. 3 classical bits can be in one of 8 combinations. 3 qubits can be a blend of all 8 at once. 4 qubits, 16 possibilities at the same time. Do you see the pattern? The number of possibilities a quantum computer can hold at once doubles with every single qubit you add. This is exponential growth. By the time you get to just 50 qubits, you're holding $2, $50 states at once. That's over a quadrillion possibilities. With 300 qubits, a quantum computer can hold more possible values simultaneously than there are atoms in the entire visible universe. This is what allows the quantum computer to look at the entire library at once. It's not actually running a quadrillion separate computations. It is performing one computation on a single incredibly complex quantum state that is a superposition of a quadrillion different values. It explores the vast landscape of all possible answers, not by walking every single path one by one, but by dealing with the entire landscape as a single entity. But this raises a critical question. If the qubits are just a big cloud of possibilities, like a room full of spinning coins, how do you get a useful answer out of it? If you just look at them, if you measure them, they will all randomly collapse into a definite state of 0 or 1. Your spinning coin will land on heads or tails. You'll get one string of zeros and ones, which is just one of the trillions of possible answers. And it will probably be the wrong one. You've lost all that rich quantum information. So how do you steer this cloud of probability toward the one right answer you're looking for? To answer that, we need to introduce our second foundational principle. one that Albert Einstein famously called spooky action at a distance. It's called entanglement. Imagine we have two of our spinning coins, our qubits. Entanglement is a special, profound connection we can create between them. They become linked. Let's say we entangle them in such a way that if one lands on heads, the other is guaranteed to land on tails, and vice versa. They are now two parts of a single system. Here's the spooky part. We entangle them, and then we separate them. We put one in a box and fly it to the other side of the galaxy. Now we open our box here on Earth and we stop the coin. We measure it. It lands on heads. At that exact instant, we know, with absolute certainty, that the coin on the other side of the galaxy has just landed on tails. This information arrived faster than the speed of light. It was instantaneous. It's not that a signal was sent. It's that the two coins were never truly separate entities. Their fates were intertwined. Measuring one immediately defined the state of the other. In a quantum computer, entanglement is the invisible thread that links qubits together into a powerful cohesive whole. It allows the state of one qubit to depend on the state of another, creating intricate, complex superpositions that are far more powerful than what you could get with independent qubits. This web of connections allows for more sophisticated operations, letting the computer explore the problem space in ways that are deeply correlated and structured, not just a random fog of possibilities. Superposition gives you the vast space of possibilities, but entanglement helps you navigate that space in a meaningful way. Which brings us to the final and most clever piece of the puzzle. We have our qubits in a giant superposition of all possible answers, and we have them linked together through entanglement. We still have the problem of finding the one needle we're looking for in this cosmic haystack. The solution lies in our third principle, interference. You already have an intuitive understanding of interference. Think of ripples in a pond. If the peaks of two waves meet, they combine to form a bigger wave. That's constructive interference. If the peak of one wave meets the trough of another, they cancel each other out. That's destructive interference. In quantum mechanics, possibilities can behave like waves. Each possible answer in that vast superposition has what's called a probability amplitude, which can be thought of as a wave. A quantum algorithm is a masterfully choreographed sequence of operations, a dance of qubits. The goal of this dance is to manipulate these waves of probability. The algorithm is designed so that the waves corresponding to all the wrong answers interfere destructively. They cancel each other out, their probabilities dropping to zero. At the same time, the waves corresponding to the right answer are guided to interfere constructively. They build on each other, their amplitudes growing larger and larger. So you start with your qubits in a uniform superposition, where every possible answer is equally likely. You then run your quantum algorithm, which is like sending a complex series of ripples through this pond of possibilities. The wrong answers cancel each other into silence, while the right answer becomes a giant, roaring wave. Finally, at the very end of the computation, you measure the qubits. You look at the spinning coins, and because of this carefully engineered interference, the probability of them collapsing into the correct answer is now overwhelmingly high. It's an astonishingly elegant approach. A classical computer finds an answer by brute force, checking every wrong door until it finds the right one. A quantum computer doesn't check the doors. It subtly nudges probability itself, causing all the wrong paths to vanish and leaving only the correct one behind. It finds the needle in the haystack not by inspecting every piece of hay, but by making the entire haystack disappear, except for the needle. So let's assemble our machine. We start with the first principle of the quantum world, superposition. Instead of a bit that is 0 or 1, we have a qubit, like a spinning coin, that is a blend of both. This allows us to create an exponentially large computational space to explore. Then we use entanglement, the spooky action at a distance, to create sophisticated correlations between our qubits, weaving them together so they can perform complex tasks as a unified system. Finally, we apply a quantum algorithm, which uses the principle of interference to cancel out the waves of probability for all the wrong answers, while amplifying the wave for the right answer. When we finally measure our qubits, the right answer is revealed. This is the real story of quantum computing. It's not magic. It's a different kind of logic, built on the fundamental rules of the universe at its smallest scales. It's a machine that computes with probability waves and possibilities instead of definite zeros and ones. And this brings us to the final, crucial part of our story. If this is so brilliant, why don't we all have quantum laptops? Why is this technology still largely confined to experimental labs with machines that look like futuristic chandeliers, housed in giant refrigerators? The reason is a single, formidable enemy, decoherence. The quantum states of superposition and entanglement are incredibly, exquisitely fragile. They are the spinning coins. The slightest disturbance from the outside world, a stray magnetic field, a tiny vibration, a change in temperature, is enough to look at the coin, and the moment the universe looks, the spinning stops. The superposition collapses. The qubit decoheres from its quantum state into a plain old classical bit, A0 or A1. All that rich quantum information is lost, and the computation is ruined. It's like trying to perform a delicate symphony in the middle of a hurricane. The quantum computation needs to be completely isolated from the outside world. This is why quantum computers are housed in extreme environments. They are cooled to temperatures colder than deep space, just fractions of a degree above absolute zero, to minimize thermal vibrations. They are shielded from all forms of electromagnetic radiation. The challenge for quantum engineers is a race against time. They have to initialize the qubits, perform the entire quantum algorithm, that complex dance of interference, and measure the result all before the system decoheres. For most current systems, that window of time, the coherence time, is measured in microseconds. This is also why quantum computers are so prone to errors. Decoherence is constantly introducing noise into the calculation. A huge part of the work in the field is developing sophisticated error correction codes, essentially finding ways to use many physical qubits to create one more robust, logical qubit that can withstand some of this environmental noise. So when you see a headline announcing a new quantum computer with a higher number of qubits, the number itself is only part of the story. The real questions are, how long can those qubits maintain their quantum state? How resistant are they to errors? And how well can they be entangled and controlled to run a useful algorithm? Building a quantum computer isn't just about stringing qubits together. It's about creating and maintaining a tiny, isolated universe where the delicate rules of quantum mechanics can play out undisturbed. Today, we started our journey with a black box, a piece of technology that felt like magic. It promised to reshape our world with computational power beyond our imagining. We looked at the promises, the cure for intractable diseases, the creation of revolutionary new materials, the breaking of our most secure codes. It seemed too good and too strange to be true. We opened that box, and we didn't find incomprehensible complexity. We found a few new rules. We found that by going down to the fundamental level of reality, we can build a machine that operates on a different logic. We replaced the first principle of classical computing, the bit, the reliable on-off light switch, with a new first principle, the qubit, our spinning coin, a component that embraces the uncertainty and potential of the quantum world. From there, we saw how the principle of superposition allows a small number of qubits to hold a universe of possibilities. We saw how entanglement weaves those possibilities together into a single powerful system. And we saw how the subtle magic of interference allows us to choreograph a computation where all the wrong answers simply cancel themselves out, leaving only the truth behind. Understanding this doesn't require a degree in physics. It requires a shift in perspective. It requires accepting that the bedrock of our digital world, the certainty of zeros and ones, is not the only way to process information. There is another layer to reality, a layer that operates on probability, potential, and connection. The quantum computer is our first real attempt to build a machine that speaks the native language of the universe. The challenges are immense, and a true, fault-tolerant quantum computer capable of changing the world may still be decades away. But the journey itself, the very act of trying to build it, forces us to confront the deepest rules of reality. It's a reflection of our own relentless drive to not only observe the universe, but to use its fundamental principles to build something new. It teaches us that the next great leap in technology may not come from making our current tools smaller or faster, but from starting over with a completely new set of first principles.
You've been listening to First Principles. Until next time, stay curious.